Hello and welcome to the 2025 Mobility Solutions webinar series. So first I'd like to introduce myself. My name is Rebecca Bell-Chambers. I'm a Senior Research Analyst here at S&P Global Mobility within the Battery Thermal Automotive Supply Chain team. And alongside me I have my colleague Hugo Cruz, who is a Senior Analyst in the Battery Automotive Supply Chain team. Today we're covering Batteries Unboxed, exploring the latest trends in pack and enclosure and design, as well as thermal management. So I'm going to hand over to Hugo, who's going to take us through some poll questions to begin.
Hi, Rebecca. Thanks for the introduction. It's only a single poll question, and I would like you to give you like a few seconds to reply to this question. I know it's kind of complicated, but what I want you is to determine with what design aspect of the battery pack enclosure do you think has the most significant impact on its material selection. A, safety and durability, B, size and weight, C, cost, or D, thermal management. I know that we are lacking an option that says all of the above, but I would like to push you to select one in this scenario. Please use the options allowed there to select an option, and we will review the poll results in a few seconds. Thank you for voting. We are approaching 50% of the participation. So I will move to the following slide once I have 50% of participation. So we are almost there. I will provide just a few seconds more. Okay. Thank you a lot for participating in this survey. A lot of you have replied that safety and durability is the most important factor when deciding what material to use regarding the battery pack enclosure. In second option, we got cost. And finally, size and weight. So indeed, safety and durability, it's one of the most important parameters. And if regulations mandate, then it is a must. So we will analyze during this presentation some trade-offs between the materials that are part of the tray and cover. So please bear with me as we will analyze some of these factors and how do they influence the battery pack enclosure design. So again, repeating, the presentation today is Batteries Unboxed, exploring the latest trends in pack and enclosure design and thermal management. And this is part of a solutions webinar series. We will have webinar series following weeks. So we will present you at the end, which will be the following webinar series in case you're interested. So in the agenda, we will cover several topics today, but it's divided in two main parts. The first one is the battery pack enclosure trends, in which we will start by analyzing our forecast regarding light vehicle and propulsion. Also, we will analyze the battery pack sizes according to the vehicle type. We will also analyze some things regarding the cathode and how the battery pack is positioned within the vehicles. Also, we will present to you our battery pack enclosure service, and we will do a comparative analysis of the battery pack enclosure materials. We will finalize this section with an analysis, a quick analysis on the fast charging evolution. The second part, to be covered by my colleague Rebecca, has to do with the role of thermal management in electric vehicles. She will also present our market analysis in battery cooling and battery heating and some integration trends. Important to mention to you that what we are going to present to you comes from our databases at S&P Global Mobility. And we will be presenting to you information from two domains. The first one is the battery domain, in which we have different products available to you. The first one is high voltage battery, in which we monitor the traction batteries that go into electrified vehicles, whether they are like PHEVs or fuel electric vehicles. We will present part of our information from this database today. And we also have our battery pack enclosure, also information that we will present during today's presentation. But we also have available other products, such as the low voltage battery, the battery raw materials, the carbon footprint, and some information on the medium and heavy commercial vehicle batteries. The other domain, thermal, we also have different products available to you in case you're interested. The first one is battery thermal, in which we monitor the technology and supply chain for the cooling and heating of the batteries that go into vehicles. Also, we have this second product called All Electric Range, in which we monitor the influence of electrical loads in the range of electric vehicles. How these loads affect the range of vehicles in kilometers. We also have other products related to HVAC, to the thermal modules, to water pump and cooling module. So in case you are interested in knowing more about any of these products, you will find our contact details at the end of this presentation. So moving to the first part of this presentation, which is battery pack enclosure trends. And I hope that you will find it interesting. So here, we are going to present to you our light vehicle and propulsion forecast. First, let me introduce to you what this chart means. On the y-axis that you will be able to see is the millions of vehicles produced per year. And in the x-axis is our forecast from current year minus 1 year, which is a historical year, plus 6 years into the future. So in this forecast, we are presenting up to 2031. The colors represent the different propulsion for the different types of propulsions that we monitor in our databases. And they are divided in several categories. The categories you will be able to find in the table to the right. So the first one is battery electric vehicle. The second one is fuel cell electric vehicle. Then we have PHEV, which is plug-in hybrid and range extended vehicles. So the first ones in this category, you can see that all of them have plug-in capabilities. Then what we have in the following categories are series hybrid electric vehicle, full hybrid electric vehicle, and what we define as mild hybrid. All these three have electrified propulsion, have also an engine, but they don't have plug-in. And finally, at the end, we have those known as internal combustion engine, and also with the stop-start functionality. So having presented this, now let's go and read the chart. What we find here is that in 2024, we saw around 10 million vehicles were produced having battery as BEVs, battery electric vehicles. We expect towards 2031 that number will increase towards 20 millions. Now, the other types of propulsions, we have seen an increase of plug-in hybrids and range extenders that here are presented in red and purple. So they will increase around 8 millions, and they will reach between 12 and 15 millions towards 2031. Now, in green, we have packed together those vehicles that have electrified propulsion, but they don't have plug-in capabilities, which again are series, full hybrids, and mild hybrids. In this case, represented in green here. We also have seen an increase in these vehicles in the years to come. And what we have noticed is that while we have experienced some decrease in our forecast for electrified propulsion, we still see a positive year-over-year increase. And what we see is that the intermediate propulsions, having both an engine and electric motors, have increased its share a little bit. We still see that internal combustion engines will be produced, and this happens because the slowdown of electrification. Still, we see an electrified propulsion towards the end of the decade. So now jumping to the following slide, what I have here is an analysis on the high voltage battery pack size, that is the traction batteries that go into electrified vehicles. And the first chart that I want to present to you to the left is the battery pack capacity in kilowatt hours and how does it correlate to the propulsion system design. So you remember that in the previous slide, we presented those vehicles having electrified propulsion, but no plug-in. So they are in the first bar. And I packed them together here as series, full hybrids, and mild hybrids. So this is a box plot. And if you remember your statistic classes, the whiskers represent the minimum and the maximum. And the box represents where are the first and third quartiles. The number that I have highlighted here is the average of these vehicles. So for this very first categorization, what we have is that the maximum battery pack capacity that we are going to be able to find here is 2 kilowatt hours, and the average pack capacity is below 1 kilowatt hour. So most of these vehicles have very small battery packs. When we move to the following category, which is fuel cells, and in the previous slides, I am just going to go very quickly to it because I forgot to present this. We almost don't have any fuel cells in our forecast. So just to provide you that as a context, now let's return to the slide that we were presenting. So these volumes that you can see here are very small for fuel cells. In any case, let's analyze them. The average pack capacity for these vehicles is below 11 kilowatt hours. For plug-in hybrids and range extenders, we have average pack capacities of 20 kilowatt hours and 40 kilowatt hours. And the limit that we find, the maximum capacity that we find, is around 70 kilowatt hours if we will draw a line from the range extender to the y-axis. And this is understandable. We don't need a very large battery pack as we still have an engine that functions with gasoline or diesel. So it will be complementary. That is not the case for fully electrified vehicles, BEVs, in which we have a very different capacities ranging from 15 kilowatt hours up to 205 kilowatt hours, with the average being in 2025 for all this chart being below 75 kilowatt hours. If we were going to take this last box plot, this last column, draft it according to the vehicle size, that's how we get the second chart. And in this second chart, what we have is the battery pack capacity only for fully electrified vehicles according to the global sales segment. And this represents the vehicle size according to the European framework, in which A is the smallest and E is the largest. So as expected, the small vehicles can only accommodate small batteries, and the large vehicles can accommodate larger batteries. So what we can see here is that vehicles in the A segment cannot accommodate batteries larger than 60 kilowatt hours. B segment cannot accommodate batteries above 80 kilowatt hours. And C and D, they start having more flexibility about the capacities that they can have into the vehicles, having the most variability for D and E segment. In our forecast, we present H vans or heavy vans in another category because they cannot be considered as segment E, and we see a smaller capacity. And this has to do with how these vehicles are being utilized, which are usually made for deliveries. So in this case, what we find is an average of 85 kilowatt hours. Now, jumping to the following slide, what we have here is the module configuration by battery pack size for light vehicles produced in 2024. So that is last year. So in the y-axis, we have the million of light vehicles with traction battery installed. And in the x-axis, we have the battery pack capacity in kilowatt hours. So starting with the first category, we only have cell-to-pack configurations. And this is understandable. These packs are relatively small, and we don't need a lot of modules for these vehicles. When we move to the following two categories that are below 5 kilowatt hours, a lot of these configurations go into vehicles that require power cells and also leverage on the modules that were built for this segment. So the packs that belong to this segment are actually the modules for the following two segments. Now, let's jump to the following categories from 5 to 20 and 20 to 40. So what we see here is that the cell module pack configuration is losing some ground against the cell to pack. And this happens because at these stages, what OEMs want is to provide consumers with the high energy density at a pack level to improve their driving range. So at 20 to 40 and 40 to 60, we start watching in our forecast that cell to pack is starting to take some market share. Also in the 60 to 80, we have seen in the previous year that cell to pack is gaining market share in order to provide these benefits to the consumers. But in the segments above 80 to 100 or 100 and more, cell module pack still becomes again the dominant configuration for on how to install the cell into the pack. And this happens because, as you can imagine, the weight starts to increase, and therefore some configurations consider still the use of modules to provide this structural protection to the modules within the pack. So what we see here is that the key, how can I call it? The takeaway that I want you to take from here is that from 20 to 80, we will see a lot of like cell to pack configuration in the years to come. And below and above 80, what we will see is a lot of like cell module packs. Just before jumping to the following slide, we have two other categorizations here, which are like cell body and cell module body. In this case, what we imply is that the cell goes installed into the pack, but the pack serves as an integral part of the structural part of the chassis. So it provides some, not only provides protections to the cells, but also provides some structural support to the chassis. While in our pack definition, this will only imply that the pack is only meant to protect the cells. Jumping to the following slide, very similar to the previous one, but in this one, we are analyzing the battery pack size according to the cathode group. And just to walk you through, in blue, we have lithium iron phosphate. In yellow, we have nickel, cobalt, manganese with some aluminum variants. And in gray, we have lead acid, nickel metal hydride, and sodium ion. Having presented that, what I want to present to you in this one is that the very first three columns below between 0 and 5 kilowatt hours are dominated by NCM chemistries. And this happens because of the high specific power that they can provide. So fast charging and fast discharging for these vehicles, it is what is required. However, above 5 up to 60 and even 80 kilowatt hours, what we are starting to look at is that LFP batteries are taking a large part of the market share. Why? Because the energy density and also other technical attributes of this cathode chemistry have improved in the last year. So they are dominating in this market, in this vehicle segmentation. However, when we go above 80 kilowatt hours, what we see is that NCM appears again. And this happens precisely because of the energy density. Still, LFP cannot be on par with NCM. So when we have very big battery pack capacities, what we see is that NCM is dominating. However, I just want to let you know that this was for 2024. If you would like to know what happens in the years to come, the detail, well, we can present to you that information in a future session, or you can contact us to determine your future strategies. Going to the following slide. Here we have some categorization on where does the high voltage battery pack is installed into vehicles. So we have like 4 main categories, which one is the engine compartment. The second one is the cabin. The third one is the trunk. And finally, we also find a lot of that batteries on their floor. So in this slide, we are analyzing where do the batteries are installed in these vehicles. First, starting with those vehicles having a very small battery pack capacity. I hope you remember how much it is, but it was like below 2 kilowatt hours for series, full hybrids, and mild hybrids. So what we have found is that here the battery can go installed anywhere in the vehicle, in the cabin, in the engine compartment, in the trunk, or even on the floor. And this happens because well, the OEM have a lot of like flexibility on where they can go, but it's also according to their necessities. But since the battery is like very small, it can be installed in any of these sections. When we move to the following categorization for plug-in hybrid and range extenders, what we see is that most of the batteries, and as you remember, some of them are even reaching like battery capacities up to 60 or 70 kilowatt hours, they need to go on the floor. We will still find some of them in the trunk and some of them in the cabin. When they are installing the cabin, what we have noticed is that they go below the seats, either in the rear seat or in the cabin or in the driver's seats. Finally, analyzing battery electric vehicles, what we find is that most of the batteries are installed on the floor. We have a small percentage, and this is this very little line that you can see here, but it's like below 1%, that belongs to the other categorization and is mostly the trunk. And this is understandable. On the floor is the best position to put these battery packs because of like the dynamics of the vehicle, and also, well, mostly because of the dynamics of the vehicle and the chassis design. So now to present to you some information, our battery pack inclusion component forecast, which is a product that we have available to you in case you're interested. In this one, we provide market intelligence on the pack, tray, and cover, and we cover both the part of who is supplying this material, who is supplying who, and the technology, what materials are being used. And it is composed by three main parts. One is the battery pack, and the battery pack is defined as, well, it considers the integration of the cells and modules as well as in the vehicle chassis. We also monitor the battery pack enclosure tray, and we also monitor the battery pack enclosure cover. Who supplies it to which OEM and which material they are using in their design for both the enclosure tray and enclosure cover. So the following slides that I am going to present to you derive from this forecast. But before jumping into that, we are making here some qualitative analysis on the material trade-offs for the battery pack enclosure. And I want to list to you first that these are the 5 most used materials that we have found being used for the battery pack enclosure, either for the tray or the cover. The first one being aluminum, the second one being steel. The third one is glass fiber reinforced polymer, GFRP, but in our forecast, it's called as SMC, which is sheet mold compound, and this is because it's the most preferred way to manufacture it. So if, in case you see SMC in the future slides, I am referring to glass fiber. Also, we have carbon fiber reinforced polymer, CFRP, and plastic. So now we will make an assessment on some technical perspectives for these materials. First, regarding lightweight, the ones that are faring the best are CFRP and plastic, and the heaviest one is steel. However, when we jump to the mechanical strength, what we find is that steel is the one providing the best mechanical strength, followed by aluminum, and plastic. And with plastic, we mean like thermoplastics is not faring that well. Then we have regarding thermal conductivity, and thermal conductivity might be something, high thermal conductivity might be sometimes desired by OEM designs and sometimes not so much, but aluminum is the one having the best thermal conductivity, and then the polymer and plastic versions not so much. Now, regarding corrosion resistant, this is only that metallic materials struggle with, so aluminum and steel do not fare that well, and of course our polymers and plastics, they don't struggle with this condition. So something to consider for designs. Even now that it is expected that some batteries will outlast the lifetime of vehicles. Moving to the following category, which is fire resistance, we are considering here the thermal runaway. And this is important because, as we have seen, the temperatures that are being generated during thermal runaway are quite high. So some materials cannot withstand it. And traditionally, aluminum and plastic cannot withstand it, and steel can. And that's why we will see in our numbers that we will present now that steel is being used a lot for the covers in a lot of vehicles. Finally, and this depends on how the battery pack and the cells within and all the electronics components were designed, it depends how much these components will be producing some electromagnetic interference to other components. So in some cases, some OEMs or some designs of the battery pack enclosure might require some electromagnetic shielding. So due to the metallic properties of aluminum and steel, these ones are faring the best, and plastic faring the worst. Now, I need to make a disclaimer here. This is a qualitative assessment, okay? So it's based on average values from interviews, media, and papers. So please bear with me as this not consider like all the alloy ratios, all the hybrid combinations these materials can have, if some materials could have like some surface treatment or some other design. So maybe in some considerations, having like some surface treatment or coating, some of these materials might fare better than others. Now, from a manufacturing perspective, which is different from the previous slide, which was technical. Well, at the end, both of them are technical, but I wanted to divide it like into categories. We are going to analyze like the raw material cost and the manufacturing cost, and steel is the one faring the best. followed by aluminum and plastic. And the one that is not doing so well is the carbon reinforced polymer. It is the most expensive battery pack enclosure material that is currently available in the market. Going to the following two categories, they have to do with the throughput and complex geometries. Aluminum fares quite well regarding that one. Still only in the production time, in the production cycles, fares well, but achieving complex geometries is possible, but it's not that easy. And when we move to plastic, it's possible to achieve complex geometries, and manufacturing is quite fast. Now, regarding the polymers, we have that they can reach complex geometries, and that's why we see a lot of them being used as covers, as we will see in the numbers that I am going to present next. In the last two categories, and this is becoming a hot topic in the industry, things regarding sustainability. First one is recyclability, and the next one is emissions and pollution. So regarding like recycling, what we have is the ones faring the best are aluminum and steel, and the polymers versions are not so easy to recycle. Finally, regarding emissions and pollutions, all of them are like below well, none of them is green, but the one doing the worst is CFRP. And not because it produces a lot of CO2, but it produces a lot of like toxic materials during the production, during the manufacturing. So this is something to consider if you're going to consider this as a material for your designs. Going to the following slide, I am going to present to you here the battery pack enclosure material trends for mild hybrids, series, and full hybrids. So in this case, as the battery pack size is quite small, we see that the tray uses a lot of the materials in, well, could use any of the materials that I have just presented before. Having steel the most important component, and also aluminum that you can see here in blue, and plastic is used a lot for these trays. For the cover of these battery packs, we find that plastic is the most used material. Now, jumping to the following slide, this is for plug-in hybrids and range extenders. And remember that these traction batteries can go up to 42 kilowatt hours, mostly. And in this case, well, the batteries start becoming like heavier and heavier. So in this case, we can reach battery packs like around like even like 200 kilograms, 240 kilograms, depending on the cathode chemistry. So then we require mechanical strength and safe material for passengers. So the trade, what we see here is that around 60% of the market share is taken by aluminum, with the remaining 30% taken by steel. We see here still some polymers with SMC and CFRP having like around like 5% of the market. Regarding the cover, we still see a lot of like different types of cover being used in our forecast, with steel taking around like 50 to 40% of the total market share. Aluminum is still being used as a cover for these segments. And we see that SMC, again, I repeat, this is glass fiber reinforced polymer, is being used with around 10% of the market share. We have other materials. In other, we are defining here as those novel hybrid materials in which we cannot determine which material is dominating over each other. And we find here like around like 4% of not applicable. In this case, not applicable, we found some designs in which some models where the battery tray is directly installed under the chassis, and then the chassis performs as the cover. And this is the case for some vehicles produced in China, and mostly in China, but also in other parts of the world. Finally, for battery pack enclosures for battery electric vehicles, these are traction batteries up to 205 kilowatt hours. So in order to not compromise vehicle range, most of these vehicles are using aluminum as the tray. Some others are still using steel, taking around like almost like 15% of the total market share. And regarding the cover, what we see is the other way around. Steel is the dominating material for this component, with aluminum taking like around 20% of this total market share, glass fiber composites taking like around also 20%, and the remaining being not applicable, CFRP, plastic, and the other novel materials that I was commenting about you before. Again, we see that steel is used a lot, and this has to do with the capability, well, with the requirements, well, the trade-offs that we presented about the steel before. Steel is very good to withstand thermal runaway, but also it offers like the adequate technical characteristics to be used as the cover in combination with the aluminum tray. Now, this is my last slide, and in this one, I want to present to you how the charging values are evolving for vehicles. So in the y-axis, I want you to see that we have the peak DC charging power in kilowatts. This at the vehicle side, not in the grid level side. And in the x-axis, we are plotting the battery pack capacity. So each of these dots, it's a vehicle that is being produced in this year, in 2025. So I just want you to look at this dot that we have here in the top, which is the BYD Tank L, that is reported to have a DC charger of 1,000 kilowatts. And it is known that this vehicle has a battery pack capacity of 100 kilowatts. So if we were going to divide this 1,000 by 100, what we get is 10. And that's how we are like doing some crude calculation. I know that it needs to be refined. It depends on a lot of factors, but that's how we are getting these lines of the charging rates. So this is the maximum charging rate that these vehicles can achieve at a certain moment during their curves of charging. So this is 10C, then we have 12C here. So if this chart will have a life and it will move dynamically through the years, what we will see is that the points are increasing and start going up and up, increasing from charging rates from 1C to 2C to 4C. So this happens because both the battery technology is evolving, but also the DC charging technologies are evolving, and this allows achieving like faster C rates and the fast charging of the battery. However, this is the takeaway for this slide. This advancement necessitates the development of effective cooling and heating strategies. And having mentioned that, I give the word to my colleague Rebecca for her to present these thermal management trends.
Thank you very much, Hugo, and thank you for the comprehensive overview of the battery pack and enclosure technologies. Okay, so I'm going to dive into a crucial yet sometimes often overlooked aspect of vehicle design, which is the thermal management. So unlike traditional ICE vehicles where the focus is mainly on cooling the engine for optimal performance, thermal management in electric vehicles is a much more complex challenge. Now, in the world of EVs, the thermal management system does have a critical role to play. And one of its primary responsibilities is to keep the battery at an optimal temperature. Now, this involves heating the battery in cold conditions or cooling it down in events such as rapid discharge, high ambient temperatures, or fast charging scenarios. Now, it's important to note that ambient temperatures can have a significant impact on driving range, and therefore the thermal management system must effectively mitigate these effects to enhance the performance. For instance, efficient battery cooling and preconditioning are essential to ensure safe and efficient fast charging. But that's not everything. That's not the whole role of the thermal management system. It also needs to manage the cooling of powertrain and power electronics, all while ensuring that the passengers are enjoying a comfortable climate inside the cabin. So as we can see, effective thermal management is not only just about the battery, but it's a comprehensive approach that impacts the entire vehicle. So when we talk about battery operation, it's important to understand that the optimal temperature range of a battery is quite narrow, and it's often more narrow than the surrounding ambient temperatures. So this means that there are scenarios where both battery heating might be needed and there are scenarios where battery cooling might be needed. And it's essential for maintaining the battery's performance. Now, in extreme cases, ambient temperature around the world can fluctuate anywhere from minus 40 degrees to over 40 degrees. I hope that none of you are in any of those climates, but it is possible. And if the battery is exposed to any of these temperatures, specifically below or above the ideal range of approximately 15 to 35 degrees, if it's below that range, we can see reduced performance unless we engage some form of battery heating. And on the flip side, if the battery temperature exceeds this optimal range, we face the risk of battery aging and even in some cases thermal runaway, which is a serious safety concern. So that's why battery cooling is crucial. And like I said before, it's about keeping the battery within that optimal range to ensure that it can operate safely and at its most efficient. So if we start by exploring the various different battery cooling methods currently available, we can categorize these into several subcategories. The two main being air-based cooling, which is also known as passive cooling, or liquid-based cooling, which is also referred to as active cooling. And today we're going to focus on those main two categories. So air-based cooling encompasses methods like natural ventilation and forced convection, and these systems are typically used in vehicles with smaller batteries that have lower thermal demands. And while air-based systems are simple and cost-effective, their cooling capabilities are somewhat limited. And this makes them, like I say, suitable for vehicles with minimal thermal requirements. On the other hand, we have liquid-based cooling systems, which include both direct and indirect cooling methods. So this might be seen in immersion cooling, in indirect coolant loops, or direct refrigerant loops. And while liquid cooling systems are more complex and generally a little bit more expensive, they do offer significantly superior cooling performance. So this makes them the preferred choice for larger batteries where effective thermal management is more critical. So if we start to take a look into some of the data presented on the chart, we have the chart here on the left, and we can see the percentage split between active and passive cooling systems. And again, just to clarify, active cooling meaning the use of coolant or refrigerant, and passive cooling meaning forced air or ventilation. Now, as we analyse the data, we can see that in 2024, approximately 65% of electric vehicles were equipped with active battery cooling systems, and this figure is projected to gradually increase to 72% by 2030. And if we move on to the chart on the right, we can break this down further into the different cooling strategies used in electric and hybrid full vehicles. And the predominant method for battery cooling is coolant, and we expect the share of the coolant-cooled vehicles to rise steadily to reaching about 60% by 2030. Interestingly, we're also observing a decline in the use of forced air and ventilation cooling. Now, this trend is largely being driven by the increasing thermal demands of electric and hybrid vehicles, which in turn are a result of larger batteries being used to support longer driving ranges. And this is a demand that's mainly driven by consumer wants. Now, lastly, it's worth noting that the market share for refrigerant is also on the decline. BYD, for example, has been known for its preference in using direct refrigerant cooling due to its efficiency and simplicity. However, as we start to look towards the end of the decade, it's anticipated that BYD will phase out this cooling medium in favour of coolant cooling. And then if we take a minute to examine the battery cooling medium categorised by battery capacity, this is where we can observe that as battery capacity rises, so does the thermal demand. So starting with the 0 to 50 kilowatt hour battery capacity band, we find that while coolant is the preferred cooling medium, this segment also shows the highest percentage of forced air and ventilation cooling. Now, as we discussed earlier, passive cooling is a suitable option for entry-level electric vehicles with smaller batteries to help keep the costs down. However, as we start to move towards larger capacity bands, it becomes evident that passive cooling is insufficient for higher thermal demands for the larger batteries. For instance, in the 50 to 100 kilowatt hour and the 100 to 150 kilowatt hour capacity bands, we start to see a significant shift. And in these bands, the forced air and ventilation cooling are virtually absent, with coolant cooling becoming the dominant method, or is already the dominant method, And like I said before in the previous slide, this is because coolant cooling provides the most effective solution for managing the battery temperatures in these larger systems. Interestingly, within the 50 to 100 kilowatt hour capacity band, we also notice the use of refrigerant. And like I mentioned before, this is thanks to a few OEMs like BYD who have been using refrigerant simply because of the system simplicity. Additionally, with no need for a water pump, refrigerant systems are lighter and safer, especially since the refrigerants are non-conductive. They're also theoretically more efficient because they do allow for direct cooling without the need for an intermediate chiller. However, there are drawbacks to this approach, particularly with regarding to complexity when trying to heat the battery. And this complexity is one of the main reasons why we haven't seen direct refrigerant being widely adopted, and why we do think that BYD will move away from this strategy towards the end of the decade. And then we look at battery cooling medium split by production region. There's some more interesting trends to observe. Firstly, we see that the majority, again, of the refrigerant demand coming from Greater China, mainly driven by BYD. On the other hand, a significant portion of the demand for forced air cooling comes from North America and Japan/Korea. Now, in North America, the demand is largely attributed to the higher number of hybrid vehicles as opposed to full electric vehicles, which, as previously mentioned, they tend to have smaller battery capacities, and this is more favorable for air cooling systems due to the lower thermal demand. And in Japan and Korea, we also observe a strong demand for entry-level battery electric vehicles with smaller battery capacities, which further drives the need for forced ventilation systems in these markets. So this trend really does highlight how different regional preferences and vehicle types can significantly influence the choice of cooling technologies. Now, another cooling method that I haven't touched on yet, and I'm sure lots of you are thinking about, is immersion cooling. While immersion cooling does offer significantly superior cooling potential due to it being able to directly submerge the cells within the battery and provide far superior cooling, as I just said, it's still a technology that hasn't been widely adopted. The main reasons for this is because of system complexity, cost, and the additional weight added to the vehicle. And because of this, we do not have a significant market share for immersion cooling in our forecast, with the demand failing to reach even 1% by 2030. And we do believe that immersion cooling technology will remain present only in high performance niche applications only. Another reason for this is also the advancements in battery technology, such as the introduction of solid state technology, for example, which will be mitigating the needs for immersion cooling systems, simply making them unfeasible. So if we move on now to discuss heat pump technology, as I mentioned on my first slide, heat was a free byproduct in ICE vehicles. However, heating in an electric vehicle is a very energy intensive process, and this directly affects the driving range of the vehicle. Now, if we look at the chart on the left-hand side of the slide, we can see the average WLTP driving range reduction in a cold climate for battery electric vehicles. The blue dots that we have here indicate conventional heating versus the yellow dots, which are showing vehicles with a heat pump system. So what we can see is that with conventional heating in a cold climate, the WLTP range losses can be as high as 20 to 30%. Now, this is really, really critical, especially when consumers are looking at the rated WLTP range versus what they're actually achieving in their cold climate. You start to get very unhappy consumers. This value is, however, slightly reduced with the use of a heat pump, so where the average loss is roughly 10 to 15%. And due to these reduction in losses, it's no surprise that the demand for heat pumps is steadily increasing. So if we look to the chart on the top right, we can see that 25 million heat pump systems will be installed in electric vehicles by 2030. Now, we do observe several different configurations of heat pump systems. This includes air-to-air, which is the most common due to a fairly simple design and installation, as well as a small package space being required. An example of this can be in the Nissan Leaf. We also observe air-to-coolant, which can be seen in the BMW i3, coolant-to-coolant, and lastly, coolant-to-air. So when we look at electric heater technology choice, we can clearly see that high voltage PTC coolant heaters are the dominant choice. Now, PTC coolant heaters are light and they're compact, and they provide quick heating to either the cabin or the battery. Secondly, we have thick film heaters, which have been growing in popularity in previous years due to their ability to generate large amounts of heat in a relatively efficient manner. And then other technology choices include tubular heating, as well as a small volume of low voltage PTC heaters. And for air-based cooling systems, the primary electrical heater choice is a high voltage PTC heater. Now, the role of electric coolant pumps is becoming increasingly critical, and they play a vital role in maintaining the optimal temperature of various different systems within the electric vehicle, and this includes the battery, the electric motors, and the power electronics. And the demand for electric coolant pumps is increasing at a rate that is faster than the electric vehicle growth. So we can see that from 2025 onwards, on average, vehicles are fitted with at least more than one electric coolant pump. And by 2030, the distribution of vehicles that are fit with 3 or 4 electric coolant pumps starts to grow significantly. And then lastly, with more complex thermal management systems, the demand to integrate the thermal management solutions is on the rise. And as we look at the demand growth for the integrated thermal management solutions, we can observe a fairly significant growth trajectory here. So in 2020, the demand for an integrated thermal management solution was fairly limited at around just 0.1 million units. However, our forecasts indicate a substantial increase to 0.9 million units by 2025 and an impressive leap to 3.9 million units by 2030. So this means that half of the battery electric vehicles produced in Europe in 2030 will feature an integrated thermal module of some capacity. Now, we are observing different methods of integration, which include the coolant module integration, either in the reservoir as seen in the Hyundai eGMP platform, or in the manifold, which can be seen in the Porsche Taycan. And we also see refrigerant module integration with the hose assembly seen in the Volkswagen MEB platform, or in the manifold as seen in the BYD E platform 3.0. And then lastly, we do see some levels of full integration, which can be seen in the cases of some Teslas, for example. So that concludes the thermal management portion of the webinar. Hugo, I can see that we have some questions coming in. So if that's okay with you, I'll fire one straight over to you. And I'll ask you, what types of materials are being used for battery housing in vehicles with battery swapping?
Before answering this question, I want to invite you, if in case you have any question that you would like to be answered in the minutes that we have remaining, we have this Q&A box. So please feel free to send us your questions, and we will try to do the best to reply during the remaining minutes of the session. Now, going back to your question, what we have seen regarding battery swapping is that the battery pack enclosure requires to be sturdy enough to handle this. I mean, battery swapping is started to be used mostly in China, but we have seen a lot of steel enclosures being used for this. Why? Because steel provides this mechanical rigidity, and also to be this material is that will be more sturdy to handle when you are doing battery swapping. So this is a material that we are using battery swapping, but also some polymeric materials such as glass fiber composites are also being used a lot. Aluminum is also feasible. However, what we have seen is that the machinery that is required, or the methods, needs to be more careful managing it's still possible, but it implies more capital expenditures increases at the level of the infrastructure required to do the battery swapping. Now, let me see other questions that are related to thermal, Rebecca. There is one here. What do you see being the biggest thermal management challenge for batteries in the coming years?
That's a good question. Thank you. I would say it's something that you touched on, Hugo. I would say fast charging is going to be one of the biggest challenges in the coming years. You mentioned, we're now seeing in 2025 10C charging coming from China, and I dread to think how much quicker these are going to get, right? And in what volumes. So fast charging is one of the key features which is enhancing the convenience of electric vehicles, but it also does present a significant thermal management challenge. When fast charging, a considerable amount of current does flow into that battery in a short amount of time, and this generates a lot of heat. So as the charging speeds are getting faster and faster, and OEMs are pushing those speeds faster and faster, I think that's going to be the biggest challenge for thermal management systems coming forward. If the thermal management system is unable to keep the battery cool enough during the fast charging, we've either got damage to the battery happening, or simply the system will slow that charging speed down. And so it's kind of pointless being able to offer 10C charging if the actual system can't keep up with that. So, Hugo, I've got some more for you. What maintenance challenges do you foresee for battery pack enclosure technologies?
Complicated one, but what we see, for example, in there are like different challenges. One will be like regarding the maintenance. I assume the question has to do with the aftermarket part, no? Like how they need to be like substitute or repaired. So I assume that, well, most of the challenges will have to do regarding the fact that it is expected that the battery pack will outlast the vehicle lifetime. So if that is the case, then this battery pack could have a second life. Now, the challenges will come more on the side of the cell and the modules and how they can be repurposed either for recycling or like a second life use. But for the battery pack enclosure, I assume that most of the battery packs that are made of aluminum or steel will be recycled because it can be used as a raw material for other processes. Additionally, you can think of like, unless you find very similar vehicle having the similar needs, this battery pack enclosure could be reused. However, that will be unlikely that it will happen. The recycling challenge will come with the polymeric materials. As we saw in the material comparison chart, the glass fiber and carbon fiber and even plastic, they present challenges in recycling. And regarding like repurposing to provide like an extended life, I think that's easier. I mean, the battery pack enclosures are not, how can I call it, a rocket science technology. So I guess like if like some damages start happening to these components, it should be possible still to repair them. I think the challenges for like maintenance for like battery packs will come when the cells get damaged, when the BMS gets damaged, the module level, what are you going to do? But regarding the battery pack enclosure, the repurposing of the materials should be possible. Most of the times it's going to be recycled if it's metallic materials, but if it's polymers, the recycling will be challenging because yes, a lot of the times the raw materials that you get are not so valuable.
Brilliant, thank you. Just before we move on, we can see we should have asked this as a poll question, Hugo, but somebody's asked best battery form factor. So maybe everyone can write in and tell us what their favorite form factor is.
Yeah, thank you for this answer that has just arrived recently. I guess like there is not I guess with form factor, well, I don't know if you are, I mean, probably you can specify in the Q&A what you mean, because we have form factor at the size of the battery pack. We have seen this kind of like prismatic shape that we call hexahedron. We have also seen these flat shapes as battery packs that go like under the cars. But also, like if we go at the level of the cells, I don't know if you're implying like cylindrical, pouch, or prismatic. So if you could like specify in the Q&A to be able to reply, that would be great. Now, assuming that we are speaking about the battery pack, because this chat was about the battery pack, I wouldn't say that is the best battery form factor, but best battery pack form factor, but the one that we have seen the most is the flat hexahedron. Because it's the only one that can be fitted below the light vehicles that, you know, in our forecast, it's below 6 tons. It's the one that goes below the chassis, between the wheels. Is the most used form factor for battery electric vehicles because of the dynamics of the vehicles and because of the weight of the battery. So I couldn't say that it's the best battery pack form factor, but it's the most used pack form factor. And okay, do we move to another question? I hope I was able to reply that one.
Yeah, it looks like we haven't had that person come back in the chat, so I think maybe we'll close the Q&A there. But please, if you have asked any questions or you have any more questions to ask, please do send them in, and Hugo and myself will be sure to follow up with you after the session. So get your questions in, and yeah, we'll be in touch. But we want to thank you, everybody, for joining the session today. As Hugo mentioned at the beginning of our session, this is a webinar series, and our upcoming webinar is on the topic title of Navigating the Future, Trends in Propulsion Technology and the Impact on Supply Chain Through the EV Transition. And this will be held on the 23rd of October 2025. So please use our QR code to register and to have a look at our program list and program calendar of all of our upcoming webinars. And please be sure to tune in to any of them that seem suitable for you. If you'd like to get in touch with us, if you want to discuss any of the topics that we've talked about, if you are interested in any of the component forecasts that Hugo mentioned at the beginning, please do contact us. We have askmobility@spglobal.com email address, as well as our various corporate sites located below, as well as our QR codes, which have our LinkedIn group, our mobility YouTube, and our various different WeChat channels. So thank you once again for joining, and we hope everybody has a great day, and we'll be in touch soon.
Thank you, everyone. Have a nice day.
Thank you. Bye.